Limiting reactants. So here I'm playing off of the old saying that the buck stops here. Well, we need to figure out where the buck stops. So in a reaction, we need to find what's causing the reaction to stop. And that's what limiting reactant is. So let's run through kind of something you're maybe more familiar with, grilled cheese sandwiches. So if you got 10 pieces of bread, 7 slices of cheese, and you're making grilled cheese sandwiches, and we're making just single cheese slice sandwiches here. We're going a little skimpy, but just to make things a little bit easier. How many sandwiches can you make? All right, so if you think about it, you can only make 5 sandwiches. All right, and so the question is why? Well, you run out of bread. And so we would look at it this way, just kind of taking it and trying to apply it to chemistry. Take something that's pretty obvious if you think about it. Let's take it and apply it to chemistry and see if we can understand how a limiting reactant works. So when we look at this reaction, we got 2 pieces of bread plus 1 piece of cheese gives me 1 sandwich. I've taken grilled cheese sandwiches and made it into a chemical reaction. All right, so we know that the bread runs out first, that I can only make 5 sandwiches with the bread. And so we would say that the bread is the limiting reactant because it limits how much we can make. All right, it basically runs out first. All right, then we would call the cheese the excess reactant because we're going to have 2 pieces of cheese left over. All right, so these are terms that we're going to use in chemistry. So taking it over and turning it into the chemistry side. So for a chemical reaction, we're going to need to see how much each reactant can make. That's generally how this is going to be given to you. You're going to be given your starting materials. Hey, you got this much of this chemical, and you got A amount of chemical 1, and you got B amount of chemical 2. Which one's the limiting reactant? And we've got to figure it out. And you can't just simply say, oh, it's the one that's the least. Well, that's not always going to be the case. It's going to be which one makes the least. So this is always going to require 2 separate calculations. And just like with percent yield, in limiting reactant, our numbers have to be in the same unit in order to compare them. That'd be like saying, hey, this many pieces of bread made this many peanut butter sandwiches, and this much cheese made this many grilled cheese sandwiches. I can't really compare peanut butter sandwiches to grilled cheese sandwiches. They're not the same thing. I need to go to grilled cheese sandwiches and grilled cheese sandwiches. I need to compare them the same way. Okay. So you can choose what unit you're going to go to unless the problem asks for a specific unit. Okay. And then whichever one makes the least is the limiting reactant. There are other ways to do this, but I find this to be the easiest. There's another way to do it where there's only one calculation, but it's a lot harder to interpret and a lot more likely for people to get wrong. I find that this way is the simplest way to understand what's going on and get the right answer. So let's look at an example. Example 1a. So what is the limiting reactant if you start with 31.5 grams of lead 2 nitrate and 6.2 grams of hydrochloric acid in the following reaction? So you're always going to be starting with reactants. And your answer is always going to be a reactant. That's the whole point. It's limiting reactant. So it's always going to be one of these two is going to be your answer. Okay, never give me one of these. All right. But like I said, what we're going to do is we're going to convert both of these to one of these products. And then we're going to compare the amounts that they make. And so in this case, I'm going to convert to moles of lead chloride. So converting to moles of lead chloride, just using stoichiometry, so grams to moles, and then moles to lead nitrate to lead chloride, gives me this many moles of lead chloride for the first one. And then converting hydrochloric acid the same way, I get 0.085. Now, why did I choose moles instead of grams? Well, because it's one less calculation. It's one less step. I could have gone to grams of lead chloride, but I would have had to put an extra step here. And why would I want to do that if I don't have to? And so if they don't specify what unit you need to go to, like they don't say, hey, and how many grams of HNO3 would be made? If they said, hey, and then how many grams of this would be made, you need to convert to that. But in this case, I wasn't told. And so I just randomly picked one of these two, and I picked this one because it was first, and also because there was a 1 in front that I didn't have to worry about. And then I just went to moles because that just makes it simpler. Now, looking at the two amounts, one makes 0.095, one makes 0.085. So this one makes the least. This is my least amount, and this is what made it. So hydrochloric acid is my limiting reactant. All right, you can then follow up this with a follow-up question that would look something like this. How much lead nitrate is left over after the reaction in example 1? So we can do this where we can figure out how much of the excess reactant is left over. So the way we do this is we convert, well, we know all of this is used up. And so what we do is we take this and we convert it to this to know how much it reacted with, or how much of this got used up by all of this. All right, and so that's what we need to do. So we do our calculation, and we get that we used up 28.1 grams of lead chloride, just going grams of hydrochloric acid to moles of hydrochloric acid to moles of lead 2 nitrate to grams of lead 2 nitrate gives me this. So I started with 31.5, I used up 28.1, that means there's 3.4 grams left over. All right, so in everyday life, we run into things that are limiting and excess. So just give you real life examples real quick. Matches. The match runs out before the oxygen in the air runs out. Rust. The iron runs out and disappears before the oxygen in the air disappears. That kind of thing. We oftentimes do things in excess. That's pretty standard practice. So that we only have to really worry about one measurement. All right, let's look at another example and see if we can just continue to get a little bit more comfortable with how this works. So what's the limiting reactant if you have 11.75 grams of zinc and 0.65 moles of hydrochloric acid in the following reaction? How many liters of hydrogen are formed? This is an example of when a question gives you a unit, and you don't have to convert to liters of hydrogen. You could go to moles of hydrogen. You could go to moles of zinc chloride to compare. It will still work, but you're giving yourself more work to do. You're going to have to go to liters of hydrogen anyway for this question. You might as well go there now just to save yourself the hassle. All right, so that's how I would do this. So I would take both of these initial amounts of reactants and convert them to liters of hydrogen. Now I can compare the amount of hydrogen that is made. And so this one makes the least, which means that is the zinc is the limiting reactant. And because it's the limiting reactant, I know this is how much is made. I can't make this amount. No, so I can't make this much hydrogen because I run out of zinc first. And I run out of zinc after I make this much. So that's how much is actually formed. That's the whole point of limiting reactant. All right, so that ends our stoichiometry unit. Just go in the workbook, practice, ask questions, come to office hours, and make sure you understand this, and I will see you in the next unit.